Hi, class. So what we're going to talk about today is unsaturated hydrocarbons. And if you remember, unsaturated is just a term for something that has a double bond or a triple bond, right? So you're just missing the maximum amount of hydrogens, right? So when we say something is saturated, it's saturated with the total amount of hydrogens it can have. We make these double bonds or triple bonds by losing hydrogens. And I'll show you what I mean. Down here at the bottom, if we had a CH3, so if you compare that molecule in blue I just drew, it has 6 hydrogens and 2 carbons. If you look at your double bond, it only has 2 hydrogens on each carbon, so giving you a total of 4. And so the way we make that double bond is we have to lose 2 hydrogens and put 1 double bond in its place. And so that's where that term saturated or unsaturated comes from. All right, so if you have a double bond, I think we talked about functional groups before that we have alkenes, right? So an alkene is anytime you have a double bond, and an alkyne is anytime we have a triple bond. A couple things about the structures. So if you remember, an alkene has a hybridization of sp2, right? Because it has a carbon with only 3 things. So it's going to be sp2. And then it's going to have a bond angle of 120. And then if you remember, the molecular shape is trigonoplanar, so it's going to be completely flat. And so that's what the second picture shows you, that if we rotate this up, it's completely flat. Right? Triple bonds, really nice because they're straightforward in terms of it's exactly flat or linear or straight. So it just goes straight across. Okay? It's going to have 2 pi bonds. Right? So the triple bond has 2 pi bonds, where the double bond only had 1. All right, so remember, the first bond made between 2 atoms is a sigma bond. Each additional bond is a pi bond. And then the hybridization of the carbon would be sp. And then the bond angle is 180. So kind of building on what we've already seen, right? We've kind of seen these molecules a little bit, and now we're just going to dive into them a little bit more deeply. All right, so while this next formula isn't specific to double bonds, it's a good way to identify double bonds. So one of the things you're going to have to do is try to identify molecules, unknowns, and we're going to look for information everywhere we can, and then kind of put that information together to build out our molecule. One of the ways we can find information about it is the hydrogen efficiency. And so this utilizes the formula. So what we're going to look at are 2 different numbers. So we're going to have our hydrogen reference and our hydrogen of our molecule. All right, so when we're looking at hydrogen reference, we have the formula down here highlighted in blue. And this is what it would be like for an alkane. All right, so just a plain hydrocarbon, no ring, no double bond, no nothing, just an alkane that's just a linear chain. And it's always going to have this formula of CN 2N plus 2. Href is that number there. It's going to be the 2N plus 2. All right, so that's where we're going to get that number. N is going to come from the number of carbons in your molecule. All right, so typically I'll give you a formula, and whatever that number of carbons is, that's what you're going to plug in for N. Okay? So that's why this Href is always going to be based on the number of carbons that your molecule has. And then we can use the number of carbons and translate that to how many hydrogens it would have if it's an alkane versus what your molecule has. Okay? The reason we're going to use this is it's going to be able to tell us if we have any rings or pi bonds. All right, so every ring is going to count for 1 hydrogen efficiency. Every pi bond is going to count for 1 hydrogen efficiency. So if you get a molecule with 3 hydrogen efficiencies, it means you have some combination of that. Either 3 rings, 1 ring, and 2 pi bonds, 3 pi bonds, any combination. One thing I want to be careful about is if you have a triple bond, Don't forget that it has the sigma bond in the middle, but then it's going to have 2 pi bonds. So you would need a hydrogen efficiency of 2. So we'll go through this and we'll work a few of these, but just make sure that every time you're looking at this, that you kind of think about, okay, what does that hydrogen efficiency actually mean? Every number we get, so if we get a number of 1, that means we have 1 either ring or pi bond. All right, the next thing we're going to do is we're going to take into account the number of halogens, oxygen sulfurs, and nitrogen phosphorus. So if your molecule has a fluorine, chlorine, bromine, iodine, so a halogen, right? So it's in that group 7, so a halogen. You're going to add 1 to your molecule. Right? So if we're building out this formula, you'd add 1 for every halogen. All right, so if you have 2 halogens, all right, so if you have 2 halogens, then you're going to add 2. If you have 10 halogens, you add 10. So you add 1 for each halogen. All right, the nice thing about oxygen and sulfur, we do nothing. All right, so we can just ignore them. So if you have 10 oxygens, doesn't matter. And the way I memorize that is that oxygen looks like a 0, so you're adding 0, which is nothing. So you can just ignore them. All right, for every nitrogen or phosphorus, you're going to subtract 1. So we'll come up here, and so we'll subtract 1 for each nitrogen or phosphorus. All right, and so what I would almost think about is you're going to do this kind of 2 ways. So we're actually going to erase this parentheses, and we're going to put a bigger one here. So when you're doing these calculations, you want to do this first. All right, so figure out your H molecule, and then you can subtract the 2. And then after that, you'll divide everything by 2. All right, and the reason we have to divide everything by 2 is it takes the loss of 2 hydrogens to make 1 double bond, or it takes the loss of 2 hydrogens to make a ring. All right, and the reason we count for rings too is if you think about a straight chain, that end of the carbon is going to be a CH3. If you loop them together, you lose those 2 hydrogens on the end to sew them together, and so you never have that CH3s on the end. All right, so let's give this a try.